So, students, I hope everybody is fine. And and in this video, we will be talking about a particle which is in a three-dimensional box, and we will subject this problem. We will subject Schrodinger's wave equation on this problem, and see what are the results of applying Schrodinger's wave equation to the problem of particle in box. Now, what we have basically is we have a three-dimensional box, and it has uh, it has walls which are ridged, and and the particle is inside this box, and this particle is free inside the box. Say this is Lx, and then say this is Ly, and this is Lz, and this particle is free inside the box, and it can hit the walls of this box, and and rebound back. It can bounce back, and these walls are assumed to be extremely hard. That it's impossible for this particle to cross these walls. So if I have to translate this problem, what am I doing here is that I have a particle. This particle can be a gas molecule, an atom. So I'm assuming a particle here, and this particle is confined to this rectangular potential box, and with the edges parallel to x-axis and y-axis and z-axis, the lengths I have taken as Lx, Ly, and Lz. And inside this box, the potential is equal to 0. So V is equal to 0. But suddenly, when the particle reaches the boundary, there's a sudden rise in the value of potential, and this sudden rise in potential, it acts as the boundary for this particle, and this potential remains infinite for the particle at these walls. Now, so the potential at these boundaries is extremely large everywhere outside the boundary that we have, and therefore this particle will be bounced back under all circumstances, and it will strike either of the boundaries. It will hit the boundary and come back and hit another boundary. Now, if I assume that the mass of this particle is m, okay, so let me take its mass m, and its total energy is E. So E is its total energy. So I can immediately write down Schrodinger's wave equation for this particle, and that will be square psi plus 2m by h cross square E of psi equals 0. Because V is 0 inside the box, so that's why the potential energy term is not included in the equation. And we can, in the similar fashion, write down this differential equation as dou 2 psi by dou x2 plus dou 2 psi by dou y2 plus dou 2 psi by dou z2 plus 2m by h cross square E psi is equal to 0. And we can see here that this psi is the function of x, it's the function of y, and it's the function of of z, and we would again like to use the variable separable approach that we had used in the previous video, where we were subjecting Schrodinger's wave equation to a free particle, a particle which is absolutely free, where there is no potential at all, and and say this psi is the function of x, x of x, y of y, and z of and z of z. In the similar fashion, we will take the double derivative of this wave function, and we will have we will have a differential equation. We will have a differential equation. Yeah, what we will have is 1 by x dou 2x by dou x2 plus 1 by y dou 2y by, this is y, dou y2 plus 1 by z dou 2z by dou z2, and then we will have plus 2m by h cross square e of nothing, because we have divided the equation by x of x, y of y, and z of z, not divided, actually multiplied, and we will get rid of this psi here, and this is equal to 0. And going back in the similar way, we have to make use of a constant here in order to make sense out of this equation. So I will take this thing equal to minus 1 by y dou 2y by dou y2 plus 1 by z dou 2z by dou z2. It has to be minus, then minus 2m e by h cross square. This is the situation, and in the similar fashion, what we will do is this 1 by x dou 2x by dou x2 will be subjected to some constant as kx. And we will go along with the same procedures for all the three cases, and we will have three separate differential equations. And what these differential equations will be, we will have a differential equation in terms of x alone, and that will be dou 2x by dou x2 plus 2m by h cross square ex of x is equal to 0. And then we will have another equation, del 2 y by dou y2 plus 2m by h cross square e y of y equals 0. So we will have these three set of equations, independent equations, where we have solved this kind of thing in detail in the previous video when we were discussing the free particle, where we used this variable separable approach. So the third equation we can immediately have is dou 2z by dou z2 plus 2m by h cross square e z is equal to 0. Okay, so these three equations, one in terms of x, another in terms of y, another in terms of z, they have the general solution. So if I take the case of the equation along x, so I would like to write the solution for this differential equation. So if I presume that solution is the solution of x differential equation. Okay, what will be its solution is x of x is equal to, say, a sine of some bx plus c. Now, this a, b, and c, these are the constants, and we have to evaluate their values using boundary conditions and using normalization. Now, to put on, if you see this equation here, as I said, that this a, b, and c, they are simply constants. Now, if we think in terms of probabilities in quantum mechanics, what we have is, according to quantum mechanics, we have psi square. What is psi square? It basically represents the probability of finding the particle. Because in our case, we have a particle that's going along x, y, or z. So here, this psi square will give us the probability of finding the particle. That should be the case, right, at any point within this box. So therefore, I should say that this x of x that I have, if I have its square of its magnitude, which is function of x coordinate only, it certainly represents the probability of finding the particle at any point along this x-axis. So this is what x of x, the magnitude of x square would mean here. And what we have is that the potential at the walls is very high, and the probability of finding the particle at the wall will be zero, because the potential of the wall of the box that we have considered is extremely large. So what's going to happen to my function here, x of x? This x of x, if I think in terms of its square of its magnitude, that should be equal to 0 when x is equal to 0, or when x is equal to Lx. This is the edge of the box, okay? And this is the start of the box along x-axis. So in that case, neither the particle can be found at the edge of the box. In both the cases, we have the edges. The only difference is the dimension, the origin that is chosen here. So what does this mean? It means that this x of x that I have should also be equal to 0 at x is equal to 0 and x is equal to Lx. So this should be the case. So this boundary condition should be used in the solution that's proposed for the differential equation that we have in terms of x of x. So when we do that, so when we use the boundary conditions, so using boundary conditions, okay, boundary conditions, and the boundary conditions are clearly defined here. X of x is equal to 0 at x is equal to 0, and x of x is equal to 0 at x is equal to Lx. So in that case, what are we going to get is, here I will have 0 is equal to a sine then b, x is 0 plus c. So at x is equal to 0, what am I going to get is this a sine of c will be equal to 0. Now this a is not equal to 0, so I can say this sine c is equal to 0. No, sine c is equal to 0. And similarly, I can say that at x is equal to Lx, I can say that sine of Blx plus c is equal to 0. So from here, c is equal to 0. I can use c is equal to 0. Now, which will yield me that sine of b Lx that I have is equal to 0. So this Blx, because sine of something equal to 0 means sine of n pi, so Blx will be equal to nx pi. because I have sine of theta equal to 0. That means sine of theta is equal to sine of n pi. So theta is equal to n pi. So this BLX will be nx pi x. Right, and this, what is this n from this equation point of view? It's an integral number. It's a positive integer, and this b that I'm looking for here, this b will be nx pi by lx. Okay, so what we have achieved from here is we have got the value of c, and we have got the value of b, and c is 0 and b is nx pi by lx. Now I would like to use the value of c and this b in the equation that I have chosen as the solution for this differential equation. Suppose this is a. So what should I do is I should use them. This is my 4, so I should use them in the original equation. So what I will get is x of x is equal to a sine of nx pi x by lx. So this is going to give me the amplitude of, this is going to give me x of x, which is a sine nx pi x lx. And we can see in this equation we have this a, and what is this a? This is a constant, and this constant can be calculated by making use of the normalization condition. So here we are supposed to use normalization. So what is normalization condition? It is integral minus infinity to infinity psi star psi dx is equal to 1. Now in my case, I have instead of psi, I have x of x. So it's a real function. So what I will have is integral. The limits will go from 0 to lx in this case. So that will be x of x square of dx is equal to 1. Now what is this x of x that's calculated out there is, it is integral 0 to lx. This is a square sine square, then we have nx pi x by lx. Then we have dx equal to 1. All right, so what can we do? We can get this a square out, and we have inside the integral, we have sine square theta, and for sine square theta, I will be using 1 minus cos 2 theta, as we have evaluated that integral in the previous videos. So what will I get here is I will write 0 to lx, a square is out, this will be 1 minus cos 2 nx pi x by lx, this whole thing divide by 2, okay, and dx of this is equal to 1. What I have used is sine square theta is 1 minus cos 2 theta by 2. So we understand that the integral that's linked with this cos, because you will get it in terms of sine of n pi, and then finally this integral dies out. What we get is a square. After integration, we get a square 1 by 2 from 0 to lx is equal to 1. So here what we'll get is a square lx by 2 is equal to 1. So what does this mean? This means a square is equal to 2 by lx. And what will be the value for a? That will be under root of 2 by lx. So this, what we have done is we have used the condition of normalization to calculate the value of A. So, so I can write down my wave function in terms of x of x. So what will be that wave function? That will be the normalized wave function in terms of x and normalized wave function. So what will be that? That's gonna be x of x is equal to under root of, instead of a, I'm going to use 2 by lx, and then sine of nx, then I have pi, and then I have x divided by lx. So this will be my normalized wave function along x coordinate. And if we find out the double derivative of this wave function along x, what will we get? So finding the double derivative. So double derivative. What will I get here is I will get dou 2x by dou x2 is simply sine will go to the cos, then cos will come back to sine, then you will originally have the original function minus times. This will be nx, then pi by lx. This will be whole square, and then again you will be back with your x of x. All right. So if I make use of this this double derivative of the wave function along x, what am I going to get in the original equation is minus nx pi by lx whole square x of x, okay, then plus 2m by h cross square ex of x that we have. This is again the same thing, x of x is equal to 0. All right, and we can evaluate this ex, and this ex will come out to be, it will simply be nx square. When you translate it on the other side, this x of x will be taken off, this x and x will be taken off. What you'll be left with is nx square, then you will have h square here, divide by 8, and then you will have mlx square. So this will give us the equation for the energy of this this particle in the box along x-axis. And in the similar fashion, we can solve this the y part of the wave function, and we can solve the z part of this wave function. And what we will come up with is, by symmetry, we can say here, so if I write down here ex again, ex is nx square h square by 8m lx square. So in case of ey, I should be able to get ny square, then h square divided by 8m ly square. And similarly, I should get for ez equal to nz square h square by 8m lz square. So that should be the case. And what we can do is that we understand that the total energy can be the sum of ex, ey, and ez, and this will give us the allowed energy values for the particle that is inside this box, which is infinitely hard at its edges, that it's impossible for the electron for the particle that we have chosen to leave this box. And that energy will be if we write down it in terms of this, so h square will be out, then we will have 8m out, and we will have nx square by lx square plus ny square by ly square plus nz square by lz square. So here we can understand that the value of the energy that this particle will have, it will have some specific values in the box. And this nx, ny, and nz, they simply denote any set of three positive numbers. And we can write down the wave function. We can write down the wave function for this whole three-dimensional, for this particle in this three-dimensional box. And that wave function is what? That is sine of that is psi of psi, which is basically the function of this nx, ny, and nz as x, y, and z. And we can write down this wave function as okay, in every case you will have 2 root 2, so I'll get that 2 out. Then I'll have root of 2 by lx, ly, and lz. Then I will have sine nx pi x by lx. Then we will have sine of ny, then pi and y divided by ly, and then we will have sine of nz pi z divided by lz. Now this equation will give us the what I call as nx, ny, and nz, or which will turn out to be quantum numbers when you'll do the problem of hydrogen atom. So here it is x, y, and z. So this thing is a representation of the wave function. And what we find is that that the energy of the particle inside this box is quantized. I mean, it can only have some specific values inside the box. It cannot have all the possible values that we can think about. So to move on, if we have to, if we'd like to have the normalized wave function for this particle in box, then certainly we will have the wave function, and the expression of the wave function here can be plotted, and we can have the results, and we can define these results at say x1, x2, and x3, and we can have the interpretation of these results. Now at the same time, if I use this, if I go with the general formulation here, En is n square h square by 8 ml square. Now this is the energy of the particle inside the box. Now I want to use this equation for a particle whose mass is, say, whose mass is 100 grams, and this box has a dimension. It's a cubical box, say, and it has L equal to 10 centimeters. Now I want to use this energy equation that I have obtained for the microscopic particles. I want to use it for some macroscopic particle. Now here what I have is Planck's constant, and we know its value is 6.6 times 10 to the power of minus 34 joules second. So I would like to have these values in above equation, and I want to calculate this En. So what will be this En if I choose the values as n square is here and h is Planck's constant? That's 6.6 times 10 to the power of minus 34 joules second. Then we have 8. Okay, then the mass that we have considered here is 100 grams, so that will be 10 to the power of minus 4 kilograms. And then we have the length, and this length is chosen as 10 centimeters, so it will be 10 times 10 to the power of minus 2 meters whole square. So this will be it, and when we'll solve this, this En will nearly come out to be 0.34 times 10 to the power of minus 45 electron volts. So here you will have joules. You will divide that number by 1.6 times 10 to the power of minus 19. So this will be this whole thing times n square. Now, we can see that this value is extremely small. I mean, if we are going to substitute it for n is equal to 1, n is equal to 2, n is equal to 3, these energies are extremely close to each other. These are so close to each other that it's practically impossible to observe them as separate lines. That's why, in case of macroscopic ball that you will have the continuum of energies. But here, when we have this microscopic particle inside the box, it can only have some possible energies inside the box. It cannot have all possible energies. That's what is the outcome of this lecture. That's what is the outcome of this presentation. And I request you again to share the video, to like the video, and if you like, you can write down the comment on the videos.